Carry out the trash at home, though. Thank you, George. Thank you, Toby. Thank you, ladies and gentlemen, for giving me this extraordinary opportunity to talk to you tonight about the evidence for findings of human effects on climate. But before I do that, a little truth in advertising here. Let's see. I'm having difficulties advancing the slides. Let's try again here. Any ideas why the slides won't advance? Anyway, before starting off on the science, I just wanted to declare my values. In addition to being a climate science and trying to improve our scientific understanding of the nature and causes of climate change, I'm also a climber. And since the age 18, I've spent much of my life in fragile, high alpine environments around the world. And over one human lifetime, I've seen incredible changes in these places. In fact, I've spent some time with Toby, as you'll see at the end of these slides here, in the Juneau ice field in Alaska. And when you stand there in the middle of the Juneau ice field and look all around you, climate change isn't just an academic issue. It's there, it's pervasive, it's everywhere you look. So, declaring values, in addition to the scientific imperative to understand this problem, I also believe there's a moral and ethical imperative to preserve these and many other fragile places for future generations. And this is actually Toby, just above Camp 10 on the Juneau ice field. What a beautiful place, if you ever get the chance. And if you're students, go and look up Juneau Ice Field Research Project, and you can contribute to improving our scientific understanding of what's going on in places like that. Okay. In 2007, the American Physical Society came out with a position statement on climate change. And a couple of years ago, the APS decided to update that position statement. And they convened a subcommittee to look at the new scientific evidence that had emerged since 2007 and asked for 6 scientists to provide testimony effectively on our understanding of the nature and causes of climate change. And what I'm going to tell you today is essentially a repeat performance of the presentation that I gave to this American Physical Society subcommittee. The first part of it will deal with what we call fingerprinting, so trying to unravel the natural and human influences on climate change. And the second part of my presentation will deal with what's been colloquially called the pause or hiatus in global warming. I first encountered this in 2010 in congressional testimony, where one witness claimed that global warming stopped in 1998, a claim I'm sure many of you have heard. And the second part of my presentation will deal with that global warming stopped claim. Okay, I'm also going to address some statements made by the chair of this American Physical Society committee, Steve Koonin, in an op-ed in the Wall Street Journal in 2014. Professor Koonin made 3 statements, and I'm going to consider all of these. The first is, the impact today of human activity appears to be comparable to the intrinsic natural variability of the climate system itself. The second, uncertainty is a prime mover and motivator of science and must be faced head-on. It should not be confined to hushed sidebar conversations at scientific conferences. And what we're doing tonight is not a hushed sidebar conversation. And finally, Professor Koonin claimed, while the past 2 decades have seen progress in climate science, the field is not yet mature enough to usefully answer the difficult and important questions being asked of it. So I actually take issue with Professor Koonin on all 3 of these points, as I'll try and convince you. Okay, So again, part one of this presentation to the APS dealt with a so-called DNA, or detection and attribution study, that sought to understand the relative contributions of human and natural influences to recent climate change. And I'm going to tell you a little bit about this work. It was published at the end of 2013 in Proceedings of the National Academy of Sciences, a large collaboration involving scientists at MIT, folks from remote sensing systems, some of the best in the world in satellite microwave radiometry, folks at Livermore. In fact, some of my co-authors may be in the audience tonight. And here's the basic scientific question we asked in this study. Can we identify some human-caused fingerprint in the vertical structure of atmospheric temperature change as a function of latitude and altitude in satellite-based estimates of atmospheric temperature change? And then, again, sort of riffing on Professor Koonen's comment, climate scientists don't look at uncertainties. Those uncertainty discussions are relegated to quiet discussions at conferences. We wanted to explicitly look at whether identification of a human fingerprint was robust to uncertainties in the observations themselves, so in the satellite temperature data, in computer model-based estimates of the fingerprint, so the change you'd expect to see in response to human influences in the vertical structure of atmospheric temperature. And we wanted to look at whether the results were sensitive to current model uncertainties and estimates of the noise of natural climate variability. And one of the unique things about this study is virtually all of this fingerprinting work just considers internal climate variability. So the rich year-to-year and decade-to-decade fluctuations in climate associated with things like El Niños, La Niñas, and other oscillatory modes in the climate system. We wanted to look at the more interesting question of whether one could identify a human effect on climate, not only relative to that internal variability, but also relative to simultaneous changes in the sun's energy output and loadings of volcanic aerosols in the atmosphere. Okay, so first of all, a brief primer on noise in the climate system. As I mentioned, one source of noise are these internal oscillations in the climate system. And what you see here are satellite-based estimates of ocean surface temperatures during a very large El Niño, one of the largest of the 20th century. You see this heating of the eastern equatorial Pacific, similar to what's going on now in the eastern equatorial Pacific. When you have a big El Niño, it can warm much of the planet. And the flip side of El Niño is a La Niña, a cooling of the equatorial Pacific. Nothing to do with changes in the sun or changes in volcanoes, purely internal oscillations. You can think of these things as a veritable zoo of oscillations. El Niño is one example, but there are many others operating on a whole host of different timescales, ranging from months to decades or even centuries. That's internal noise. In addition to the internal noise, there are things like massive volcanic eruptions. This is satellite imagery of the eruption of Mount Pinatubo in the Philippines in June 1991. That big aerosol cloud there, those are essentially liquid phase sulfuric acid droplets that were formed in the upper atmosphere after the eruption of Pinatubo. And as I'll show you later, when you have a very large eruption like that, you reflect some portion of incoming sunlight back to space, cooling the lower atmosphere, sometimes for years after the eruption. In addition, The sun is a variable star, and we have changes, we've monitored changes in the sun's energy output since about 1979 using a variety of spaceborne instruments. And that's what you see here. You nicely see over roughly the last 35 years or so the difference between solar maximum and solar minimum. But you can see that over the time we've actually measured the sun's output from space, there's been no overall increase in that output. So all of this is purely natural. Okay, so what are the measurements we're going to look at? Beautiful, beautiful things. So the theory of trying to monitor the temperature of broad layers of the atmosphere from space using microwave emissions is 50, 60 years old. Folks recognized that by measuring the microwave emissions of oxygen molecules at different frequencies, those emissions are proportional to the temperature of broad layers of the atmosphere. And you can actually back out those temperatures for the lower atmosphere, the middle troposphere, the upper atmosphere, by monitoring at different frequencies. And what we're going to do is we're going to look at these broad atmospheric layers. This is the lower troposphere, the mid-troposphere, the lower stratosphere. We're not going to look at this purple record here because it's shorter than the other three. And what we're going to do is we're going to calculate synthetic satellite temperatures from all the computer model simulations that I'm going to show you to have a fair apples-to-apples comparison between the actual microwave observations of atmospheric temperature and the model simulations. That's a bit computationally intensive, but many people do that nowadays. They have in climate models these emulators of satellites. So you can essentially fly a synthetic satellite through the climate model output and mimic the way the actual satellite sees the Earth's atmosphere. Okay. So this is what you see here, again from our friends at Remote Sensing Systems in Santa Rosa. These are these observations of the microwave emissions of oxygen molecules. We have them from 1979 through to present. This paper was published in 2013, so that's why this record goes through to 2012. And what you see here, looking from the South Pole to the North Pole and from the surface right up into the stratosphere, right up to about 20, 30 kilometers or so, you see that over the period we've been monitoring these microwave emissions of oxygen molecules, the lower atmosphere has warmed, the upper atmosphere has cooled. The largest cooling is over the Antarctic ozone hole. Ozone itself is a greenhouse gas, and by depleting ozone through emissions of ozone-depleting substances, we've essentially caused more cooling here in the upper atmosphere, particularly over the Antarctic ozone hole. Now let's look at the simulations. These are the latest, greatest results from about 28 different models. These model simulations fed into the most recent assessment report of the Intergovernmental Panel on Climate Change. Again, what we did here is we used an emulator to calculate satellite temperatures from the model simulation output. These are all simulations that include human-caused changes in greenhouse gases. So what you can see is there's some areas of difference. So in the real world, where we've seen this profound retreat of Arctic sea ice, the warming over the Arctic in the lower atmosphere is actually larger than in the model simulations. And in the tropics, it's the other way around. The models warm more than the observations. But to zeroth order, you see this very curious dipole structure of warming of the lower atmosphere and cooling of the upper atmosphere. So the question we're going to ask in this study is, could natural causes, internal variability, the sun, volcanoes, individually or in combination, mimic this very curious dipole structure? Could chance alone give you this fingerprint? Okay. All sorts of ways of doing fingerprinting. I'm going to give you a brief sort of pictorial explanation of what it involves. So here is this model estimate or guess, if you will, of the response of atmospheric temperature to human factors. And that's the beauty of model simulations. You can do the Gedanken experiment that we can't do in the real world. You can just change human factors and then look at this fingerprint and ask, is this fingerprint increasingly evident in the observations? So essentially what we're going to do is calculate some statistic of similarity, of pattern similarity, between the searched for human influence fingerprint and this time series of observed satellite patterns of change. And that gives us some measure of pattern similarity here, and you can see that there's a trend in it. So over time, the observations are becoming more similar to this human influence fingerprint. And there's a lot of stuff that we understand about the time series here. This dip here is around the time of the Pinatubo eruption I mentioned earlier. The volcano heats the upper atmosphere, cools the lower atmosphere, which is the converse of this searched for human fingerprint. That's why you get this negative spike down here. This positive spike is the 1970 97-98 El Nino event, which warms the lower atmosphere, so that projects positively onto this fingerprint here. So we understand a lot of the features of this thing, and the bottom line question is this trend unusual? Could you get that degree of pattern similarity by chance alone? So to answer that question, you generate null distributions. So what might this pattern correlation statistic look like in the absence of any human effects on climate, but just due to natural fluctuations in climate? And again, the beauty of model simulations is you can do that world without us simulation, where you just have internal climate variability, fluctuations on year-to-year and decade-to-decade timescales, but no human-caused changes in greenhouse gases or other external factors. And you can look at many thousands of years of these world without us simulations and look at essentially distributions of how the pattern similarity between the search for fingerprint and random noise would behave. And that's this thing here. And then, you can do a very simple signal to noise analysis, and you can look at how this guy here, the actual result that we got, this is the correspondence between the search for human influence fingerprint and the satellite observations. And we're going to look over the first 10 years. That's what I'm going to call our signal. And the noise we build up by looking at all 10 years trends in that pattern correlation statistic from the control runs. That's the denominator. So you can form a signal to noise ratio, and then you just increase by a year at a time. And you can see this dip here is a result of the Pinatubo effect, that cooling caused by the big volcano. The bottom line, though, is that if you look over the entire 33-year satellite record, the signal-to-noise ratio is over 10. So it's huge. What that is telling you is that if these model-based estimates of internal climate variability are correct, then natural internal fluctuations in the climate system can't mimic that pattern of sustained, latitudinally coherent warming of the lower atmosphere and cooling of the upper atmosphere. The other thing you'll note, and again this gets back to Professor Koonin, is that there's a band about the observations. So the Remote Sensing Systems group has generated now, as is typical in our field, an ensemble of observations. Producing these satellite-based estimates of atmospheric temperature change is a tough technical job. Satellites drift, sometimes by up to 4 to 6 times over their lifetime. And that orbital drift, because of the drag of the Earth's atmosphere, affects the time of day at which they see a given location on the Earth's surface. Because the Earth has a very large daily temperature cycle, whether you measure at noon or at 6 p.m. really matters. There are other issues. This is actually a dozen satellites that are up there over this 33-year period. And even though the radiometers are engineered to be identical on the Earth in vacuum environments, in practice, when you get them into the harsh reality of space, the instruments drift, the calibrations drift as the instrument is actually heated by the sun. Accounting for all of these things is tough, and this group has generated a 400-member Monte Carlo ensemble of plausible observations, and we can use that kind of stuff to look at just the question that Professor Koonin was trying to get at there. Can we characterize uncertainties in the models and the observations, and are our results sensitive to those uncertainties? In this case, for the uncertainties in the observations, the answer is no. The results are not sensitive. And this is actually a second group at the University of Alabama, and their results are actually kind of similar to the other groups. So the bottom line is, the first part, internal variability alone can't explain this fingerprint of warming of the lower atmosphere and cooling of the upper atmosphere. But as I mentioned, could some combination of internal variability and the sun and volcanoes explain what we see? Again, the nice thing is we have simulations now from many different computer models of the climate system performed around the world where people look at our best estimates of volcanic and solar activity changes over the last 150 years. And that's what you see here. These are simulations of stratospheric temperature by a bunch of different models. These big spikes here, this is Pinatubo, this is El Chichon in 1982, this is the Krakatoa eruption. So you can run these models without human influence, but with the sun and with volcanoes. And you can also run them for longer periods of time. These are so-called last millennium runs, where the models are run from 850 AD through to 1849 with our best estimates of the solar and volcanic changes that happened over the last 1,000 years. And you can see there's some very, very large eruptions, like one around 1250 AD. In this particular model, developed at the National Center for Atmospheric Research, this eruption caused global heating of the stratosphere of nearly 14 degrees Celsius. So very, very big eruptions, much bigger than anything we've actually experienced over the satellite era. So the statistical question is, if you use this kind of information to calculate the denominator of the signal-to-noise ratio, do you still get positive detection of a human effect on climate? So you can look at that in the same way. Here's what I showed you before. These are the tests relative to internal climate variability. These are the tests relative to internal climate variability plus the sun plus volcanoes from 1850 through to the present. And these are the much larger natural noise estimates from these last millennium runs. And you can see that even in this case, if we assume very large changes in the sun, very large eruptions, larger than anything we've encountered, you still get confident detection of a human effect on climate. Why? Why is this pattern so unusual in the observations? Why is this human influence pattern so unusual? And again, I would point out that, one knock on climate models is that they don't make predictions that we can actually falsify in some kind of Karl Popper type sense. This was a prediction. So back in the 1960s, when Suki Manabe at Princeton performed the first simulations of doubled atmospheric CO2, this is the kind of thing they got: cooling of the upper atmosphere and warming of the lower atmosphere. And that was before the satellite era, before we actually had satellite observations to determine whether the upper atmosphere was cooling. He could have been wrong, but they weren't. The observations actually were consistent with this fingerprint of the effects of increases in CO2 and the effects of depletion of stratospheric ozone. So what's going on here? Well, here we're looking at these three different noise estimates: the internal variability from the control runs, the variability from these simulations that have internal factors, the sun and volcanoes from 1850 through to the present, and the variability in these last millennium runs over 1,000 years. And this is just a simple empirical orthogonal function analysis to isolate the key modes of variability in these world without us simulations. And without getting into the details, all I'm trying to convince you here is none of these things show that any combination of natural causes could give you this search for fingerprint. None of them give you anything like this latitudinally coherent, sustained warming of the lower atmosphere and cooling of the upper atmosphere. And again, physically we understand what's going on to get that human fingerprint, that if you increase CO2, you more effectively trap heat lower in the atmosphere. To restore radiative balance, the upper atmosphere has to cool. And, you know, like I said, some of the latitudinal features of this cooling in the upper atmosphere are consistent with the effect of stratospheric ozone. Largest ozone depletion has been over the Antarctic ozone hole. So to first order, we understand many of the features of these patterns, and they're directly tied to radiative effects that were predicted 50 years ago. Okay, so the first part of the talk, we did identify some latitude-altitude pattern of human-caused climate change in satellite observations. And this fingerprint could be discriminated not only from the internal noise of El Niños, La Niñas, and all of this rich zoo of internal variability, but also from total natural variability. So the combined effects of these internal factors, the sun and volcanoes. And up to that point, nobody had really examined that question. Everybody had focused on the internal variability question. And I want to stress that this significance testing framework is highly conservative. It's a sort of worst case scenario because we're testing against these world without us simulations that include volcanoes like Krakatoa and the 1250 eruptions and Maunder minimum solar irradiance changes that are much larger than anything we've actually experienced over the satellite era. So the bottom line is this, that internal and total natural variability can't produce these sustained warming of the lower atmosphere and cooling of the upper atmosphere that we see in observations and in human influence fingerprints. Okay, next section of the information that I presented to the APS, the pause in warming. So here we're looking again at these satellite-based measurements of the temperature of the lower atmosphere. So temperature changes over roughly the lowermost 4 to 5 kilometers of the atmosphere. The black line here is the average of about 28 climate models. These are very similar to essentially identical to the model simulations I just showed you. We've again run this satellite emulator through the models to produce these lower tropospheric temperatures. And you can see nicely in the models, since we're averaging over many different realizations from different initial conditions and many different models, you beat down the random noise of El Niños and La Niñas. So the black curve there is very smooth. And the pink envelope is the uncertainty on that model-based estimate of lower tropospheric temperature changes. And you nicely see something I mentioned earlier. This is the April 1982 eruption of El Chichon, which caused cooling. You see this long goodbye. When you have a big eruption, it cools not only the land surface, but also the ocean surface. And some of that ocean cooling is subducted into the intermediate and deeper ocean. And it takes time to recover from that. And you see the same thing after Pinatubo, this rapid cooling maximum cooling within about a year, and then this gradual recovery from that. Of course, in the real world, these are the satellite-based estimates, again, from these two groups in Santa Rosa and Alabama. It's much noisier than the black curve because you've only got one realization of the observations. With one particular sequence of El Niños and La Niñas, you can't beat down the noise by averaging over many realizations of the real world. So don't be disturbed or distressed by this mismatch there in the amplitude of the noise. Again, you see that this spike here is the big 97, 98 El Nino event, which I mentioned earlier. But the bottom line question is, what's happening here? So it looks like over the last 15 to 18 years or so, there's some mismatch in the warming rates between simulations and observations. The models with human-caused changes in greenhouse gases and with estimated changes in the sun and volcanoes continue to warm, but the observations apparently do not. And this apparent discrepancy has been the source of an incredible amount of scientific, political, popular discussion. What's going on here? All right. Well, those of you who are devotees of congressional hearings might have caught the data or dogma hearing in the Senate about a month ago that was convened by Senator Cruz. And at that data or dogma hearing, it turned out that the kind of figure I just showed you was item A. It was piece of evidence number 1 to support this claim that the only possible explanation for that mismatch in observed and simulated warming rates is that models are too sensitive to human-caused changes in greenhouse gases. So as I like to call it, the models suck explanation. That was the only explanation given or discussed. But in fact, there are a number of other explanations for that kind of discrepancy. And as scientists, our job is not to score political points, it's to understand, to seek the why. Why do they differ, particularly over the last 15 to 18 years? And it turns out that, imagine some higher alien intelligence gave climate scientists the hypothetical perfect climate model with perfect representation of all real-world physics in the climate system and said, here it is. This perfectly captures everything important in the climate system. But even with that hypothetical perfect model, if you ran it with incorrect estimates of how these external factors, the sun, volcanoes, human-caused changes in greenhouse gases, particulate pollution, had actually changed, you would get the wrong answer. So scientists have spent a lot of time looking at these drivers, these forcings, as people call them, that have been used in the simulations of historical change that I just showed you. Stratospheric ozone depletion, volcanic aerosols, and sulfate aerosols, essentially human-caused particulate pollution, primarily from coal-fired power plants and automotive emissions, and errors in the solar forcing. And in each one of these 4 cases, there is good reason to expect that we didn't get it right. We did not, particularly over the last 18 years, exactly describe what the real world experienced. The third explanation, and this has also received a huge amount of attention, is errors in the observations. As I mentioned, not only the satellite observations, but surface thermometer measurements have a large number of uncertainties associated with them. Satellites are not a thermometer in space, as was claimed at this data or dogma hearing. It was claimed, that satellite-based estimates of atmospheric temperature are some unambiguous gold standard that one can use to evaluate climate models. Again, as I tried to convince you, there's actually extraordinary technical challenges in producing geophysical retrievals. These are not direct measurements of temperature. You gotta use a radiative transfer model to convert from microwave emissions of oxygen molecules to an estimate of temperature. So there are uncertainties in the satellite data. There are uncertainties in the surface observations. Even today, surface thermometer measurements don't cover the entire planet. And there are concerns that we may have undersampled the Arctic, which is warming markedly over the last 20 to 30 years. So that's explanation number 3. And explanation number 4 gets back to this internal variability issue again, that the real world had one particular sequence of El Niños and La Niñas and other modes of variability. And the model simulations would not be expected to get that sequence of observed variability right, except by pure dumb luck. So you've got to account for those kind of differences and sequences of variability. And they're particularly important if you look at short, noisy periods of record, 10, 15 years or so. You look at longer sweeps of time, you beat down the influence of those differences in the precise realizations of variability. So we decided to look at one of these particular factors, the volcanoes. And this work was really inspired by Susan Solomon at MIT, who published a paper in Science in 2011 entitled "The Persistently Variable Background Stratospheric Aerosol Layer and Global Climate Change." Beautiful paper. I'd refer it to you for further study. And what Susan and her colleagues showed was that the model simulations I presented here all assumed that after the Pinatubo eruption in 1991, the stratospheric aerosol loading from volcanoes decayed to background by the end of the 20th century and remained at background into the 21st century. But in fact, that's not what happened. And this eye candy here shows you some of the recent eruptions. This is Sarychev in Kamchatka in 2009, this sort of almost atomic cloud there with a hole through the sky. This is the eruption of the Icelandic volcano with the unpronounceable name. Although I did found one guy, the guy at JERP when I was there, who could pronounce that name. I was seriously impressed. This didn't have much of a stratospheric signature, but it interfered with air traffic in Europe for a period of weeks to months afterwards. And this is Nabro in Eritrea, one of the largest eruptions in the early 21st century in 2011. And I'll try and convince you that Nabro in particular had a discernible signature in many different observational climate records. So these are these measurements from 2 different groups, from Jean-Paul Vernier et al. At NASA Goddard Space Flight Center and Makiko Sato at the Goddard Institute for Space Studies in New York. Beautiful, beautiful measurements. So these measurements look at the extinction of starlight, sunlight, and moonlight by gunk in the upper atmosphere. And these are measurements in the visible, and by measuring at different frequencies in the visible, primarily above 15 kilometers, you can back out the loadings of aerosols in the atmosphere. So primarily satellite-based measurements. There are some LiDAR ground measurements as well. And what you can see here, every vertical line is a volcanic eruption of a certain magnitude. And people use different scales for trying to assess the magnitude of a volcanic eruption. This is something called the Volcanic Explosivity Index. This big peak here, this is the effect of Pinatubo on aerosol optical depth. This very, very rapid, almost knife-edge Pinatubo got sulfur dioxide into the atmosphere and into the upper atmosphere very, very quickly, where it was oxidized and formed these liquid phase sulfuric acid droplets, and then this long decay of stratospheric aerosol after that. This is Nevado del Ruiz, and here you know, this bunch of vertical lines here, these are these small early 21st century eruptions. And you can see that the two different observational groups both show in the early 21st century an increase in volcanic aerosol optical depth. So more reflection of sunlight back to space. But they're different. They have large, still somewhat unexplained differences in terms of how they behave after Pinatubo. Some of these differences are related to things like which frequencies they measure at in the visible, how they account for cirrus clouds, because you gotta try and clear cirrus clouds from the satellite view in order to make these measurements. So kind of like the microwave sounders, many technical decisions that you have to make in producing these observational estimates of a quantity we really care about. But the kicker is this, that the model simulations assume this, flatlining. They assumed that there was no increase in stratospheric loadings of volcanic aerosols after 2000, and that was wrong. And the reason why there's this mismatch here is that Susan Solomon's paper was published in 2011 after most of the modeling groups had already performed these simulations. So this scientific insight that, wow, something really unusual and interesting happened, even in the absence of very large Pinatubo-class explosive eruptions, the cumulative effect of this succession, or as one friend of mine likes to call it, swarm of smaller eruptions, increased the reflectivity at the top of the atmosphere. And, sadly, again, that insight came after the simulations were performed that fed into the fifth assessment report, the 2013 assessment report of the Intergovernmental Panel on Climate Change. So what we did then in a recent paper is we looked at a whole bunch of observations. This is aerosol optical depth again. The vertical lines here show some of the larger eruptions. This is Tavurvur in Papua New Guinea. This thing here is the Nabro eruption that I showed you before in Eritrea. These are averages over the tropics and over a near global domain, the extent of the satellite aerosol optical depth measurements. And we also have independent radiometer measurements of fluxes of long wave and short wave radiation at the top of the atmosphere. So you can see that, say, after these two large eruptions here, Tavurvur and Nabro, you have a sudden increase in the amount of short wave reflected at the top of the atmosphere because of this volcanic aerosol cloud. Completely independent measurements. These again are these microwave sounder measurements of the temperature of the mid to upper troposphere, and you can see with some lag effect this cooling that happens after the larger eruptions. This again, microwave sounder estimates of the lower troposphere. This is a completely different measurement of the amount of atmosphere, the amount of water vapor in the atmospheric column. You cool down the atmosphere through Clausius-Clapeyron. You reduce the ability of the atmosphere to hold moisture, so you get this drying effect. And finally, this is rainfall and ocean surface temperature. And I'm just going to show you then the two larger eruptions, Tavurvur in 2006 and Nabro. And you can see that there's this internal and physical consistency to the signals of these things. You can see them throughout a whole bunch of different independently measured variables and across the electromagnetic spectrum too. Microwave, infrared, visible. That's compelling. That tells you understand something. This is not a house of cards resting on one observation alone. And we were able to show in this paper and in an earlier paper in 2014 that once you cleaned up the climate variability associated with El Nino, you could clearly reveal these signatures of these smaller eruptions, and they were statistically significant. You couldn't have gotten this kind of cooling or drying signature or reflection of radiation at the top of the atmosphere by chance alone. So, the bottom line, oh, yeah, this just is to illustrate that the swarm continues. This is from last year, this beautiful image of Calbuco in Argentina. So for whatever reason, there's been this fascinating continuation to this swarm of more moderate eruptions. And Calbuco, too, likely made it above the tropopause into the stratosphere. So it will be interesting to update some of these analyses. So conclusions, we were able to show that we could identify some signal of late 20th and early 21st century volcanic activity in a whole bunch of different observational data sets. Forget about models. These volcanic cooling and drying signals are there in the observations, both for the large Pinatubo eruption in 1991 and for the more recent period. I also showed you that there are still puzzling uncertainties in these observational estimates of aerosol optical depth. The nice thing from my perspective is that this work has given impetus to the observational groups to understand why they differ. It's clearly critically important for us to understand these forcings that have actually gone on over the last 15 to 18 years, particularly these cooling effects like volcanic effects. And the bottom line is this. Again, if you get the forcings wrong, as we did in this case, you're going to get the wrong answer. So part of the reason for the mismatch between simulations and observations is neglect of the cooling influence that volcanic activity exerted on the real world over the last 15 to 18 years. Just finally, I want to show you the shape of things to come. Just 2 slides here that give projected changes in, first of all, global average surface temperature out to 2100. And I call this red world and blue world. Blue world is enlightened humanity. The assumption here is that global annual greenhouse gas emissions peak over the next 10 years effectively and decline thereafter. And you see envelopes here because this is generated with roughly 3 to 4 dozen different computer models of the climate system generated by institutions around the world. And the black line is the multi-model average there. And the red world is the business as usual world where humanity doesn't do anything to reduce emissions of greenhouse gases. By 2100, you get warming of roughly 4.5 to 8.5 degrees Fahrenheit. So a different world, a different planet out to 2100. And the sea level implications of blue world and red world look like this. Blue world, you get projected sea level increase of 10 to 21 inches out to 2100. And red, business as usual world, over 3 feet. And I stress that these are highly conservative since essentially scientists felt unable to reliably quantify the dynamic contribution to sea level rise from melting, moving ice sheets. So most of this is just the so-called thermal expansion component of sea level rise and some contribution from melting land glaciers. But you know, our ability to really effectively understand the contribution from moving ice sheets is tough. Final slide. In the real world, there's no control run. You might think that this beautiful image here is a mock-up. It isn't. So a Japanese artist attached a bonsai tree to a balloon and launched it into the stratosphere and somehow took this picture of this fragile bonsai tree in the upper atmosphere. And this picture conveys many things to me, the fragility of the atmosphere, the fragility of life, and the fact that, unlike in the model world, we don't have a control run. We only have one planet Earth, and we got to get it right. Thank you very much for your attention. Be happy to answer any questions you might have. Oh, and I should point out, I will be around tomorrow too, and I will be speaking in Toby's session tomorrow on climate change, so you can find me tomorrow too.
Dr. Santer, thanks for coming, appreciate your talk. Do we see, or do we have enough sensitivity in the carbon dioxide measurements to see the contributions of the volcanic activity to the carbon dioxide, especially in the upper atmosphere?
The CO2 contributions of volcanic activity are small, about 1/100th of the human contribution over the last 150 to 200 years ago. Now, that's not always been the case in the past. In the past, with very large fissure eruptions or the Deccan traps, volcanoes injected a lot of CO2 into the atmosphere many, many millions of years ago. But that's not the case with these eruptions here. The best estimates are that the CO2 increases we've seen from roughly 270 parts per million, 260 parts per million around the time of the Industrial Revolution to 400 ppm now, maybe 1/100th of that is volcanic.
Yes, well, I enjoyed your talk very much. Was the solar variability the sunspot cycle, and what's the cause, what's the effect? Are the sunspots the cause of the solar variability, or some other connection?
So that was, let's go back to that quickly. So what you saw there was essentially the difference between solar max and solar min in terms of the measured total solar irradiance. And those irradiance variations are in phase with the sunspot cycle. And people indeed have tried to use the sunspot cycle in order to extend this stuff back in time. So they've looked at relationships between very long Chinese sunspot records that go back centuries, or records of cosmogenic isotopes like 10 beryllium, whose abundance is related to solar activity changes. And they use these kind of calibrations over the instrumental period to extend those sunspot records and cosmogenic isotope records back in time and make inferences about how the sun's energy output may have varied on century timescales.
Thank you for an interesting talk. I have the occasional discussion with a good friend of mine who is a climate skeptic, and I have two specific questions that he always comes up with to me that I may not necessarily have the best answers for. Since it sounds like you've had the pleasure of a lot of discussion with skeptics, maybe you can help me out. The first of them is that, as in fact a thermodynamicist, he says that temperature is an intensive variable and there is no such thing as a global temperature that can be defined. And then I have to say, yeah, I guess you're right. How does one, and I would like to change to another variable. And so how would one deal with that question? And the second point that he makes is that H2O is a major greenhouse gas, which also has major variations in opacity. And he therefore claims that climate models cannot correctly incorporate H2O. So those are the two major points that he makes others, but I'll just stop there and ask for help with those. Thank you.
Sure. Thanks for those questions. First one, these satellite-based measurements of the temperature of bulk layers of the atmosphere are sort of the best global average estimates that we have. Surface thermometer measurements, as I mentioned, are patchy and change as a function of space and time. So in terms of monitoring the global scale temperature of the Earth, the satellites are probably the best that we have. That being said, there are also integrated measurements like the total heat content of the ocean that really do attempt to give some estimate of how the entire ocean has changed. We think that 90% roughly of the energy that is going into heating the planet is going into the oceans. And we have measurements from a variety of different instruments of how ocean heat content has changed. I can show you some of those results, but those are the best estimates that we have, and they're all consistent with a warming planet. The surface observations, the satellite observations, ocean heat content observations, they're internally and physically consistent. As I've showed, though, too, there are still uncertainties in each of those measurements. The second part of your question was about water vapor, and water vapor is a powerful greenhouse gas, absolutely right. And in fact, we've done some of these fingerprint studies with water vapor changes. We've specifically looked at the question of whether these observations, satellite observations of water vapor, there's this instrument called the Special Sensing Microwave Imager that looks directly at the hydrogen absorption line and gives you a pretty reliable measurement of changes in total column water vapor from 1988 through to the present. And water vapor has increased, consistent with Clausius-Clapeyron, about a 7% increase per 1 degree C warming of the lower atmosphere. And our best understanding of that increase is it's a response to the CO2-caused warming of the lower atmosphere. When you increase CO2, you start warming the surface, the lower atmosphere. Warmer atmosphere holds more water vapor, and you have this positive feedback loop involving water vapor. The curious thing about the water vapor stuff, and I'd be happy to show you our fingerprint papers where we compare the model simulation output with observations, is that the observed pattern of water vapor increase is pretty much coherent, increases everywhere, and largest water vapor increases over the warmest area of tropical oceans. And that coherent fingerprint, water vapor increases everywhere, is very different from the typical patterns of water vapor change associated with things like El Nino. So to the best of our knowledge, the observed water vapor increases that we've measured from space are not natural. They're a response, a feedback to the warming caused by human-induced changes in CO2.
So in the modeling data that you showed, you said it didn't account for the volcanic activity happening. I was wondering if there are plans, or is there a model that includes those changes in volcanic activity, and in your opinion, do you think that it would match observations?
Great question. Yes. So the answer is that the satisfying aspect of this work, from my point of view, is that this work initiated a whole bunch of observational studies to better understand the actual observed changes in volcanic aerosol over the period we've monitored volcanic aerosol from space. And then in tandem with that, the modeling groups got really interested in trying to incorporate those latest, greatest estimates of volcanic aerosol changes in simulations of climate change. So a number of groups, the National Center for Atmospheric Research, we have a paper currently submitted that looks at those simulations with our latest, greatest estimates of volcanic aerosol loadings and tries to understand how big is the effect. So what difference does it make if you include a more realistic estimate of the volcanic aerosol changes the real world actually experienced? So I can die a happy man because this work has actually demonstrably led to improvements in the observations of aerosol optical depth and to better simulations as well. And you don't often see that particular feedback loop in this kind of work, that something you do feeds back into the development of better observations and better simulations. But again, you know, the real intellectual credit for kicking the ball rolling should go to Susan Solomon at MIT.
I'm sure many people have more questions, and Dr. Santer will be available after the talk to answer your questions, but we'll have to close this session now. Can we thank our speaker again?